Good morning, John. A nuclear reactor at Chernobyl exploded. This kind of explosion had never happened before and hasn't happened since, and it wasn't supposed to be possible. But why? Why was it supposed to be impossible, and why wasn't it? There are simplified answers out there. I'm not going to get deep into physics, but I am going to be a little bit more robust in how I talk about it because I think it's really interesting to actually understand what happened here and why. But first, an introduction of terms. Nuclear, pertaining to the nucleus, which is the center of the atom that contains the protons and the neutrons. Protons, the nuclear particle that has a positive charge. The number of protons defines what element an atom is. Neutrons, the neutral particle. Why does it even exist? Well, why does anything exist? But basically, for subatomic particle physics reasons, if you have too few neutrons in your nucleus, the nucleus will fall apart. If you have too many, the nucleus will fall apart. Why? Forces, I guess? Isotope. So the number of protons an atom has always determines what element that atom is. 6 protons, it's carbon every time. Now carbon usually has 6 neutrons, but sometimes it has 5 or 7 or 8 or 9. And so we have this word isotope to describe these different forms of carbon. So the normal carbon is carbon 12, and then there's carbon 13 and carbon 11, etc. Unstable isotope. Now, almost all naturally existing elements on Earth are stable isotopes. That's because they're stable. Unstable isotopes generally have too many or too few neutrons, and so they will emit energy or particles on their path to becoming a more stable nucleus. And that process of emitting energy or particles is called radioactive decay. Radioactive decay is one kind of nuclear reaction. There are 2 other kinds. There's fusion, where 2 atoms come together to become 1 atom, and then there's fission, when 1 atom breaks into 2 atoms. During fission, the leftover fission products, which is all the particles and atoms that are left over, are always a little bit lighter than the original atom. What happened to that mass? Well, it became energy, as described by a pretty famous equation. That energy is most of what we ultimately capture in a nuclear reactor and turn into electricity. The products of fission themselves are unstable isotopes, so they continue to decay inside the nuclear reactor. So heat in nuclear reactors is actually created in 2 ways. One, the vast majority of it is created through the fission of the atoms into smaller atoms. Secondarily, though, heat is produced by the radioactive decay of these unstable isotopes that are the product of the fission reaction. So even after the nuclear reaction stopped, this radioactive decay continues to produce heat. That heat has to go somewhere. It goes into the fuel, and if you can't keep cooling off the fuel, it will melt itself, and then it keeps getting hotter and hotter. It makes itself hotter as long as these isotopes are unstable and emitting radiation. They heat themselves up, and that can melt through just about anything, which is what we call a meltdown. Now, there is one single naturally occurring isotope on our planet that has a very special ability. Uranium-235, if you hit it with a neutron, not only will it split apart, but it will create more neutrons. And those neutrons, if they hit another uranium-235, that will split apart and it will cause this nuclear chain reaction. This is the reason why we have nuclear power on this planet. Now, U-235 is a rare isotope. It's about 0.7% of naturally occurring uranium. Uranium-238 is much more common and much more stable. So usually when we're making nuclear power or a nuclear bomb, we have to enrich the uranium. So there's much more U-235. In like a nuclear bomb, it's like 80% U-235. In that case, pretty much every neutron flying around in the thing is causing another fission reaction, which is causing more neutrons. So this instantaneously, all of the uranium fizzes. It becomes a bomb. Like it's a bomb. That's the whole point of the bomb. This is, of course, not what we want in nuclear reactors. We want to be able to very carefully control the speed of the chain reaction. Usually, a super important part of this is enriching the uranium, not all the way up to 80%, but to some more enriched version than naturally occurring uranium. It's just that enriching uranium, it turns out, is extremely expensive. So the genius-ish thing about the RBMK reactor design, the thing that people liked about it, was that it was a cheap way to use unenriched uranium, or very slightly enriched uranium, to create a self-sustaining nuclear reaction. Now, to do this, because the fissionable atoms of U-235 are farther apart, and there's other stuff in there that can absorb neutrons, you have to do more with the neutrons you have. A primary goal of all nuclear reactors is controlling neutrons. And you can do this in two ways. You can absorb them, which slows the reaction down, or you can moderate them, which speeds the reaction up. That sounds a little counterintuitive. It is. I'll explain why. When a uranium atom splits apart, the neutrons that come out are going extremely fast. They're going too fast, actually, for quantum mechanics reasons that I don't understand, to actually hit another uranium atom and break it apart. Mostly it will just bounce off. And then it'll fly out of the reactor and it won't get used. So counterintuitively, you have to slow down the neutrons to speed up the rate of reactions. To do this, you use something called a moderator. They moderate the speed of neutrons. They do not moderate the speed of the reaction. They increase the speed of the reaction. Now, there are some reactors that are able to do this with heavy water, which is like isotopically enriched water that actually makes it really good at neutrons bouncing off of it and slowing down some. That's expensive because heavy water is expensive, but the nice thing is if the reactor starts to get hot, the heavy water starts to boil, and then there's less of it around to slow down the neutrons, so the reaction starts to slow down. It's a negative feedback loop, which is the kind that you want inside of a nuclear reactor. Now, the RBMK reactor used regular water as a coolant because that's cheaper, but regular water is actually a neutron absorber. That's going to become really important later. So instead of heavy water, RBMK reactors use big, heavy blocks of graphite to slow down the neutrons. That's the neutron moderator. So to sum up, you've got moderators, which help speed things up, and you've got absorbers, which help slow things down. These are your gas pedal and your brakes in your nuclear reactor. And you need these things because there's other stuff that affects the rate of the reaction that changes as the fuel is used. It changes depending how long the reaction has been going. And in all reactors, like in the fuel, you have the buildup of different byproducts of the fission. And some of those absorb neutrons, some of them slow neutrons down. There's a big one, xenon-135, which is part of the decay pathway after uranium breaks apart. So it doesn't show up immediately, it just like ramps up slowly and it starts absorbing neutrons, so you have to pull your control rods out some. There's ways to control all this stuff, but it's complicated, so you need ways to be able to put on the brakes or put on the accelerator. The xenon thing is what happened on the day of the accident. They had basically run the reactor all day in a sort of a perfect procedure for what you would do if you wanted to increase the amount of xenon-135 in your reactor. They didn't do this on purpose, it's just what happened. And so when they started to decrease the power for the test, the xenon started to suck up all the neutrons and the reactor dropped into this situation where they just weren't getting any power out of the reactor. Now, the normal thing to do with an RBMK reactor, because of all these positive feedback loops, is to very slowly bring the power back up. But they wanted to get the power back up fast. So what they did is they pulled all of the control rods out, pretty much all the control rods out of the reactor. The only things left absorbing neutrons in this reactor now are water and xenon-135. If one or both of those things go away, then you would have a nuclear reactor that is in a very difficult to control state. They talk in this show, and a lot of science communication talks about, and I completely understand this because like, you don't have however long this video is to explain all of this. They talk about how the control rods were tipped with graphite. So when they came back into the reactor, the first thing that happened is that this moderator, the things that speed up the reaction, was the first thing that came into the reactor. Now you might, having heard that version, which is the simplified version, be like, why on earth would you tip a control rod with graphite? Like there's easier, cheaper stuff to tip a control rod with. The simple answer to that question is that they didn't. Let's explain. So when you're using normal water as your coolant, it also is absorbing neutrons. So if you take your control rod out, which is the thing that absorbs neutrons, and all that's left, like water is just taking that space, you have a less good, but still a control rod made of water in that space absorbing neutrons. So in RBMK reactors, they have control rods that control in both directions. The top of the control rod is made to absorb neutrons, and then as that pulls out, it pulls in a graphite rod, and that is made to increase the reaction. This is the graphite tip. That's not actually a graphite tip. It's part of what makes the reactor work. So you have in every control rod a brake and an accelerator. And you can't do one without the other. So on the day of the accident, they hadn't just pulled out all of the brakes, they'd pulled in all of their accelerators. Pretty much all of them. This is not the biggest problem. The biggest problem is neutron flux, which is basically the movement of neutrons throughout different parts of the reactor. And you want to control the movement of neutrons throughout the reactor so that all of the fuel burns evenly, so you don't waste anything, and so there aren't areas of the reactor that are hotter than some other areas. To accomplish this, the graphite moderator rods are actually shorter both at the top and the bottom than the fuel rods. So in those spaces, there's some water, and that water is absorbing neutrons. And in the middle, you get a nice flat curve of neutron flux evenly distributed throughout the reactor. And this is fine. This is great, unless you take all of the control rods out at the same time and then put them all back in at the exact same time. And we'll see why. So on the day of the accident, they had pulled out all of the absorbers, pulled in all of the accelerators, and then you have your positive feedback loops kicking in. Specifically because the flow of water through the reactor had been slowed down, the water started to boil. Water is usually there absorbing neutrons, so it's boiling. And suddenly there isn't as much water there absorbing neutrons, which is increasing the rate of the reaction. And then finally, all of these neutrons that are suddenly flowing around eats up all of the xenon-135, so that control that had been there the whole time is suddenly gone. And then you have the final fatal decision, the thing that you're supposed to do in this situation. When the control rods started to come back into the reactor, the graphite rods displaced the water at the bottom of the reactor until suddenly there was nothing in the bottom row of the reactor that in any way throughout the entire reactor was controlling neutrons at all. So the reactor is already dangerously overpowered, and then localized in the bottom of this reactor, you have this spike of neutron flux that's beyond anything the reactor is designed for. That very rapidly increased the amount of energy being produced, and something somewhere broke. It could have been a lot of different things that in this situation broke. It might have been multiple things at once, but when it broke, it locked those graphite rods into this most dangerous of positions. And now it's time for a side note on explosions. An explosion generally seems like it has something to do with fire to us. Fire is often a component of explosions. It's why we can see them. So that's what the movie explosions look very fiery. But explosions actually happen usually when a solid or a liquid converts into a gas. And gases take up much more space than liquids. And as that rapid expansion happens, that is your explosion. That sounds wild, but it's the case. This is all about phase change. And the hotter your gas is, the more space it takes up. And so, the water in the reactor got so hot that it turned into this extremely pressurized vat of steam. So hot that in fact it dissociated into hydrogen and oxygen, which then becomes itself a fuel. The top popped off the reactor. The graphite in this environment became basically fuel, and so it caught on fire. In short, it exploded. Now, Fukushima also exploded. It exploded in a much different way. Instead of the reactor itself exploding, hydrogen escaped from the reactor, and that hydrogen gas exploded, and that damaged the reactor. Bad, but much different from what happened at Chernobyl. All of those isotopically unstable fission products were then either started melting because there was no cooling left, or they burned and went into the air for people to breathe for hundreds of miles. This sounds like a worst case scenario, and in some ways it is. This is as bad as it can get when it comes to a reactor exploding, but it is not the worst case scenario when it comes to the impact that it could have on people. There were ways after the fact that this could have gone much worse if it were not for a lot of hard work and clever engineering and bravery. But reactor design is all about creating balance. Even with all of these problems, the design of the reactor prevented anything catastrophic from happening unless you did a very specific set of things. The things that they did in 1986. If you want to get a little deeper into the physics of this, Scott Manley's video on this topic is amazing. And if you want to watch the HBO miniseries, I found that very good and enlightening in terms of the human and political causes of this disaster, as in addition to the engineering and physical causes of the disaster. John,